Hello, everybody. Welcome to today's current seminar. Today we have Shida Wang. He will be giving a talk on StableSSM, alleviating the curse of memory in state space models through stable reparameterization. Shida Wang is a fourth-year PhD candidate in the Department of Mathematics at the National University of Singapore under the supervision of Professor Lee Xianshu. Prior to joining NUS, he earned his undergrad degree in applied mathematics from Fudan University. His research focuses on sequence modeling and machine learning, language models, and nonlinear systems, with a particular interest in understanding complex map patterns and structures in data. With that short introduction, the floor is yours, and you can start your presentation.
Okay, thank you so much for the invitation, and I hope everyone can hear me clearly.
Yes.
Yeah, okay. So I'll start. Today I'm going to talk a bit more than the StableSSM paper because I think there are some necessary background. So I will give this talk named Inverse Approximation Theory of Recurrent Models. And in particular, I will care about sequence modeling scenario. So okay, so basically, there are three things in the title: inverse approximation theory and the recurrent models and the application sequence modeling. But I will try to introduce all these three things with a more concrete phenomenon, that is the memory phenomenon in or maybe human beings and the recurrent models. Because memory of human beings is a kind of interesting and important research topic, and a lot of biological or medical study has been spent on digging this phenomenon, and there are very popular results such as the Ebbinghaus forgetting curves. That's Ebbinghaus study the maintenance of some words pairs during the different time horizon, and I just borrowed the following forgetting curves from his paper. Okay, hold on a second. Seems stopped sharing. So, okay. Yes, so I am talking that I just borrowed this Ebbinghaus forgetting curves from the paper that is they are studying the forgetting of some word pairs as the timing from increase from minutes to like days. And so basically, today I'm going to discuss the learning or maybe forgetting of long-term memories, just similar to the idea of these Ebbinghaus forgetting curves. But now I'm studying the forgetting in recurrent neural networks rather than the human beings. So probably you all heard of recurrent neural networks, as it is a very classical research topics from like 30 years ago, but I will just quickly discuss the structure of these recurrent neural networks. So first, in recurrent neural networks, there will be a hidden state maintained in the model. And every time when a new input X is fed into the model, recurrent neural networks will use the input X and the previous hidden state H to update the hidden state using some function F. And as you can see, in the unfolded figure, basically the hidden state is sequentially updated based on the input and the function f. Okay, so this is the classical recurrent neural networks. And as we mentioned that we want to do the similar things as Ebbinghaus, so basically we need to find a way to quantify the memory of these models. And here in the sequence to sequence modeling setup, what we are trying to do is to measure the partial derivative of partial yt, partial xt. So here you can see given input x0 to xt, we can consider the prediction yt. So basically, the dependency of yt on xt is some short-term dependency because there is no shift in this temporal direction. But we will say that the dependency of yt on x0 is a long-term dependency, as the information in x0 needs to be stored in h0 and then passed all the way to ht and then be shown in the prediction yt. And based on this setup, we can also observe that if we consider partial yt, partial xk, for example, k equals to 2, then if there is a zero dependency of yt on x2, then it means that there is no memory in yt about x2 because changing the value of x2 does not change the prediction anymore. Okay, so this partial derivative is the way that we quantify the memory of recurrent neural networks, and now we give the more specific definition for this memory function. And here we are considering a special class of input because for general continuous input signals, the definition of the memory function is very difficult to handle the influence of other time values. So here we are just considering a piecewise linear input, like they are 0 and then they will goes to some value x as the time increase. Okay, so this is the test input that we consider, and then we just define the memory function using the previous partial derivative idea. And here I want to mention that I discussed that this is the memory dependency of yt on xt minus t, but in practice, I am measuring this dyt dt as the change of x0 is actually very similar to the change in time t, because if we just shift from 0, 0x, if this is x minus 1, x1, x0, x1 to 0, x0, then basically we are shifting from y0, y1, y2 to y1, x1, y0, and y1.
But why is that for arbitrary inputs?
This is actually not for arbitrary input because we are just considering these special test inputs here. So maybe I should include the notation for x. We are just considering that for these piecewise, or actually these are two piece input, we can define the memory function. This memory function is not suitable to generalize to any continuous input.
Okay.
Okay, so with this definition, we can have this MT defined from 0 to infinity, and then we say that the memory function is a decaying one. If as time t goes to infinity, it goes to 0, and correspondingly, we say it has an exponentially decaying one. For some positive beta, we have the exponential decaying form. Okay, so we have this memory function and the corresponding decaying property. And actually, this definition is also general in the following sense, because there is a very classical tool in functional analysis, that is for linear functional. We can use with representation to get that the output sequence and input sequence is just related by this kernel function rho. And when we evaluate the memory function of this linear functional, what we are calculating is actually just the kernel rho at time t. Okay, so which means that our memory function is defined for general nonlinear functionals, but it is actually compatible with linear functional if we want to see the memory effect in the linear case. Okay, so we have talked about the memory concept that we are interested in this talk, and then we need to proceed to the models, and then I can present the approximation theory in the third part. So basically in this talk, we are working with bounded input sequence. They are uniformly bounded, uniformly in time bounded. And the models that we are talking about is for now limited to single layer models. That is, there are three models that is relevant in this talk. That is, the first one is the linear recurrent neural networks. Basically, it just has linear hidden state dynamics and linear readout. So this model is simple in the sense that we can have explicit formula for the yk and xk, and then because this linear recurrent neural network is kind of limited, it is just linear dynamics, then we need some nonlinear activation. And the very classical nonlinear recurrent neural networks is actually the middle one. That is, people will place nonlinear activation sigma in the hidden state dynamics. And this gives nonlinear hidden state dynamics, which can help the model to learn general nonlinear functional. And the last one is a special case for state space models. That is, we are considering lambda to be just some diagonal weight matrix. And here the activation sigma is placed in the layer between hidden state and the output yk. So basically, linear recurrent neural networks is the most simple one, and the nonlinear RNN is just adding activation function, and the state space models are adding the activation in a different approach. Okay, so here is a brief graphical demonstration to show that the difference between recurrent neural networks and the state space models. So in recurrent neural networks, the recurrent activation is added in this temporal direction, while for state space models, the nonlinear activation is placed in between two hidden state layers. And the corresponding continuous time models will be the following one. They are just replacing the terms with the differential equation. Okay, and actually for this linear recurrent neural networks, as the hidden state dynamics is ordinary differential equation, so we can actually consider the typical stability of this hidden state dynamics, as we mentioned that we are working with the input sequence satisfying that they are uniformly in time bounded. Then the requirement for this linear recurrent neural network to be bounded. If we want this property, then we will require that the eigenvalue of weight matrix, the real part is negative. Okay, so this is the stability of this recurrent neural networks, and actually for state space models, since they share the same hidden state dynamics, then the eigenvalue bound should be similar. But for the nonlinear recurrent neural networks, this can be a bit tricky, and some result can be obtained for activations such as TENJ. But for general case, it is still unknown that what kinds of requirement on weight matrix W to keep the dynamics stable. And in the next part, I'm going to talk about the stable approximation. This concept is related to the stable system in the sense that stable approximation is trying to find a certain process or a numerical algorithm to find the above stable system. But now the parameters is different. The parameters to be the parameter that need to be stable is different in the sense that in stable system, we want the hidden state HT to be bounded to be stable. But now for the stable approximation, actually the state of this numerical algorithm is the trainable weight CWU. Now we want the optimization algorithm for CWU to be stable. And I will, in the later slides, try to convince you that this stable approximation setup is a good to have in the approximation setting. And to see why this stable approximation is necessary, so we need to take a step back and consider the very classical universal approximation, because universal approximation theorem is basically the theoretical foundation for the power of neural networks. And this universal approximation property is just a qualitative statement to say that whether a particular neural network has the capability to approximate the target continuous function sufficiently well. But the issue of this universal approximation theorem is that usually we cannot tell the advantages of different models. For example, we know that most of the models in sequence modeling, such as temporal convolution, recurrent neural networks, transformers, all these models, basically, they are universal as long as you increase the hidden dimension. But we cannot tell the advantages of different models just based on the universal approximation property. So we want a more fine-grained theorem to tell us what's the advantage for different models, because probably each model has the task that is suitable for the model. And we will give the definition for stable approximation using the idea of perturbation error. And the perturbation error is assuming that when we optimize the trainable weight, here it's the theta. When we optimize the trainable weight theta, we will suffer from the noise or the finite training steps, so we cannot achieve the optimal theta m star. And then we have a measure of this computation budget, because if we have infinite computation budget, then if we have infinite computation power, then we can reduce the optimization error to 0. But in practice, we will always have a positive beta, which means that this EM beta is the error that we achieve when we stop the optimization as we get close to the optimal weight. And then based on this perturbation error, we can say that the universal approximation is working with the case with beta equals to 0, because universal approximation are just talking about the property of the optimal weight at dimension m. But for stable approximation,
can I ask a question?
yes.
Okay, so you compare the difference in weights, optimal weight, which is the current weight at
Here's theta for recurrent model.
versus the cost versus computational cost. How does that make sense? They're two different things. You say theta minus theta m star in the
Yes.
L2 norm is less than beta, but beta is a measure of computational budget.
Actually, I should say that this beta is like the tolerance or the stopping criterion in our optimization. It's like
okay. So it's like
when we are sufficiently close to the optimal weight with distance beta, then we can.
I understand. It's like the epsilon distance. Yeah, okay.
Yeah,
That's what
it's
you
the
meant.
epsilon
I
distance.
thought it was different currencies. Okay.
Okay. Maybe epsilon.
It's fine.
Okay, so we can have this perturbation error, and using this perturbation error definition, now we can see the difference of universal approximation and the stable approximation. So basically, in universal approximation, we are discussing the case with no noise, with no computation budget issue. So beta is 0, and then we are just increasing the dimension from 1 to infinity, and the error goes to 0. But for stable approximation, we are actually this can be rewritten as the statement that. So universal approximation is taking the limit with beta goes to 0 first, and then m goes to infinity. But for stable approximation, the limit is taken in a different way. That is, we are taking the dimension m goes to infinity first, and the perturbation error, the perturbation scale beta to 0 next. And this difference will be seen clearly in the future slides. So here I just give this definition, the perturbation error, and the next I just collect a bit related works. That is, for classical nonlinear recurrent networks and like recent multi-layer state-space models, the property of the universal approximation is quite well studied. So therefore, people know that for nonlinear RN and state-space models, you can use them to learn the target continuous relationship. But if we consider this stable approximation, then the answer is a bit unclear. And what we are trying to do in the StableSSM is trying to give this characterization. And the answer is that for both nonlinear recurrent models and multi-layer state-space models, they cannot stably approximate some target. Therefore, they are not universal approximators. And the theorems is given in the following informal approach. That is, assume we want to achieve the stable approximation of a target using nonlinear RNN models, then the target will be limited by the following property. That is, with the same tolerance beta is greater than 0, with the same tolerance beta from the perturbation error, then the memory function of the target will be decaying exponentially. And this is the interesting aspect of this theorem. That is, if we are starting with UAP, then beta is 0. We cannot see this phenomenon as the memory function is actually just decaying. So we are working with the decaying memory target. So this theorem is actually saying nothing. But for stable approximation, we are working with the case that beta is greater than 0. Now this computation budget or the epsilon tolerance, it will comes into the limit for this memory function characterization. And very similarly for multi-layer state-space models, an exponential bound will hold for the memory function. Okay, so for recurrent neural networks, we have a qualitative statement, and for state-space models, we have the following characterization. And actually, this memory function bound tells us that the typical approach to improve the performance of neural networks is feasible to relax this curse of memory, but it is not efficient in the sense that if you want to maintain the memory function MT to be greater than some epsilon, then we need to have like L0, theta max, or PT. Is at least one of them needs to grow exponentially based on this memory function characterization. So this is why we say that there is a curse of memory.
What is the L0? Sorry, what's the L0?
Oh, L0 is the Lipschitz constant of activation.
Okay.
And theta max is the weight norm. So if we use like more precise weight, then we can have larger theta max. And this PT is just a polynomial growing function that's with order L-1. But because there is an exponential component, so there this PT is not efficient to counter the effect of e to the power of minus beta t. So basically, this curse of memory is significant for state space models. And later on, we will show that actually modern state space models, that is like the model used in S4 or Mamba, they are not the type of vanilla state space models we are talking about here. And they tries to relax these issues. And we want to study like what's the key difference to make the curse of memory go away.
So can I interpret this theorem as follows? is that all the SSM's models to be stable, they have to forget very quickly. Is that what
Yes,
this theorem says? Yeah.
yes. It's like if we want to do the optimization with some tolerance beta, then this cannot be avoided easily.
So in other words, we should not try to model non-Markovian systems with SSMs.
Uh, maybe, yeah, I cannot tell for sure.
Hi, can I reinterpret what George was reinterpreting? I think that what this says is that unless beta is equal to 0, you will start forgetting at some point, right? You cannot
Yes,
escape the loss of memory, right? That's what the theorem says. And
Yeah.
because we
yes,
can never achieve beta equal to 0, we are bound to forget,
Right.
yes,
right?
that's right.
Unless we, as the time progresses, we keep increasing exponentially the dimension of or the whatever is the
Yeah.
polynomial there, which is exponential in the number of layers, or I mean in the layers, etc. Right?
Yes. So
Yeah.
the input dimension, they are usually fixed. We cannot change it. And
Right.
the Lipschitz coefficients, I guess people are not that crazy to repeatedly tuning activation
E-
function. So
exactly. Yeah.
yeah, so the reasonable tunable component will be theta max. That is, we are working with a very large weight scale, but this can come with some other issues like the generalization issue if we are optimizing with a very large weight norm.
Yeah.
Yeah,
Thank
so
you.
in general, this can be very difficult.
Yeah. I'm wondering if there is a version that instead of having exponentially decaying memory, you can have algebraically decaying memory.
Yeah, that's the ideal case, or
Yeah.
that's at least they can relax the common statement that state-space models or recurrent models has short-term memory. Because if we have a polynomial memory, then probably
Mhm.
they are much better in qualitative sense than the exponential one.
Yeah. Thank you.
Okay, so this is the problem part that we are showing that statistic models has all these kinds of memory issues. Next, we will proceed to the part that people try to resolve this curse of memory. But before that, I will just show briefly the numerical verification of this curse of memory statement. So this table is just the completion of the previous one. We are trying to say that recurrent models and the multi-layer statistic models, they actually have the difficulty to do stable approximation. And for one example, if we have a target with memory function decaying polynomially, then using gradient-based method, which means we have positive beta, then this thing can be challenging. And there are some optimization statements for this case in a previous custom memory paper. And again, we go back to this perturbation error because we want to show this error in a numerical experiment. So we want to say that a universal approximation can be achieved and stable approximation is very difficult. And the following one is the curve that we get for a linear functional, because for the linear functional and the linear models, everything is a bit simpler than the nonlinear model, and both in optimization and in approximation. And as we can see in this figure, as dimension increase from 2 to 14, the perturbation error will goes down from this blue curve to all the way to maybe the dashed curve. So this one is trying to show that for target with exponential decaying memory, we can have a convergent perturbation error. Therefore, the approximation error, that is the corner points, that is the points on this y-axis, they are showing the approximation error. EM0. And for these curves, they are just EM beta. So to read the existence of approximation, we just need to have these points goes to 0 as dimension increase. But to have stable approximation, we need to have this curves convergence for some positive beta 0. So this is the existence of stable approximation for exponential decaying memory. But for polynomial decaying memory, such as 1 over t squared, then there will be a issue, that is, despite we can have the existence of universal approximation, that is, as dimension increase, the error at beta equals to 0 will again decrease. But now we cannot have a positive beta 0 because we can consider the neighboring lines, that is, their intersection will just goes down as we increase the hidden dimension m. In the limiting case, it will be similar to the black dashed line, that is, there is no there is no positive beta 0, therefore the limiting curves will always increase. And this can be seen that, for example, we consider beta equals to 0.1, then we can go up. As dimension m increase, we can see that the perturbation error is not decreasing monotonically. Actually, after dimension maybe 6, the error is now going up. Yeah, so when dimension m is larger than 6, the error will goes up, like from 6 to 8 to 14. So this is the issue for this polynomial decaying memory. We cannot have a perturbation error that is suitable at this 0.1 scale. And so we can show that stable approximation by the previous figure, that is, in universal approximation, what we are working with is that we will have fixed beta, and increasing dimension m is not always beneficial, in the sense that for polynomial decaying targets, we have the universal approximation, but for fixed perturbation beta, increasing dimension is not always giving us benefits. But for the case of stable approximation, we can see in the exponential memory figure, when beta is less than beta 0, we can have that limit m goes to infinity, em beta is decrease. Oh, it is decreasing as m goes to infinity in this figure. Okay, so
how do we find that beta 0 in real networks?
I don't know how to find beta 0 for a general nonlinear RM models, because actually I haven't considered like how do we identify this beta, because this beta is very crucial to evaluate.
Exactly, yeah.
Yeah, but we can have some estimate of this beta. It's like the one indicator for this beta is the eigenvalue, the smallest eigenvalue of the recurrent weight matrix. So one idea is to combine the eigenvalue range of different recurrent matrix, and then figure out whether we can estimate this beta using these eigenvalues. Yeah, but here I am working with a synthetic example, so I can construct beta 0 to make sure that everything will be a clear approach. But for general nonlinear models, it is still unknown, and I think this is an open topic to identify like what kind of decay a particular recurrent model is suffer from. That is, maybe we can identify them and then we can further improve it. And so we can see the difference of universal approximation and stable approximation based on the qualitative beta behavior. And in practice, given an optimization method, people will expect to have smaller error when they use larger model, because people use larger model, they spend more computation budgets, then it is ideal to have smaller error. But universal approximation actually does not guarantee this, because they might have issues as dimension m increase. But for stable approximation, the good news is that when beta is sufficiently small, increasing dimension is beneficial. It's like if we have enough computation budget, the scaling law is still scaling law will holds. So, but here the issue is like we don't have a characterization of this beta is sufficiently lost. Beta is sufficiently small statement. So this might be the difficulty in stable approximation approach. Okay, so I've talked about a lot of negative results for recurrent neural networks and statistical models. Now we proceed to see the positive result. That is how people resolve the cursive memory using the idea of stable representation. And in the paper of StableSSM, we actually try to identify the representations that can make the cursive memory goes away. So here we are introducing the representation on the recurrent weight matrix. So basically the rest since U and these other trainable parameters are kept to be the same. But for the recurrent weight matrix, now we have a wrapper function f. And we say f is a stable representation if the logarithm of f is uniformly continuous. So this condition, the logarithm of f is uniformly continuous, is kind of like this term is considering the effect of fw, because fw close to zero, it will means long-term memory. It can be highly sensitive. Therefore, the requirement of this logarithm fw to be uniformly continuous will help us to have a more smooth loss function with respect to this fw. And this is kind of a heuristic interpretation, but in the proof of the theorem, we can establish that for these logarithm conditions, the stable approximation can hold. And this is a figure demonstration for the stable representations. There are various different representations like the classical exponential and soft plus. They are widely used in the S4 paper. And we also consider some different sigmoid, like the different representation like the sigmoid one. And the best one is the one that is proposed in StableSSM with the best sense in the sense the best sense is that we have a uniformly bounded gradient scale. That is, we want to have the gradient to be bounded by some constant c. So this is the one that we name to be the best one. But in practice, actually, we are finding that this best case is giving a kind of marginal optimization benefit. And the reason might be that the classical exponential or soft plus is already stable enough for this scenario. Okay, so we define the stable representation, and we can have that stable SSMs. They can achieve because the representation does not change the model space. Therefore, the universal approximation property is just the same as the previous models, but the representation will change the loss landscape. Then the perturbation error is no longer the same. And for stable SSM, we prove that they can stably approximate targets. And this difference can be viewed as part of the reason that recent state space models are better than the traditional nonlinear recurrent neural networks, because like people study RNNs between 1989 to 20, maybe 17, and then transformer come, and then recently state space models, people work with it. So basically, the reason that people go from recurrent models to transformers is that they found that recurrent neural networks have difficulty to scale up to a large scale. But for state space models, right now people are training state space models with billions of parameters, and they are scaling up very efficiently. Like the result from Mamba shows that the 1 billion parameters have matching performance for transformer and state space models. So this is the
But the reason,
approximation.
hold on. The reason is because of the cost, because of linear cost versus quadratic cost. Not.
Uh,
I didn't see a discussion on the stability.
yes, actually,
I'm not
I
sure
am.
what you may.
Yeah,
I,
I need to make my idea, my point more clear. That is, people are going from transformer to state space models based on the costs. But previously, there is no reason for people to go from RN and transformer using the quadratic cost. So people go from RN to transformer based on the issue of performance. That is, for example,
that's
in
true.
the
That's true. That's true. But
for GPT-2
it,
scale, people have difficulty to do it with recurrent neural networks. Then people move to transformer. But now statistical models show that you can actually train the model with the like the 100 million parameter or 1 billion parameter. So it means that for sure statistical model is better than RNN in some sense. So this is the reason that I say that people just consider go back from transformer to state model, because the cost issue is the recurrent neural networks has a lot of like the low inference cost property, which is very nice to have.
right.
Yeah. So actually for the from the stable approximation sense, that is we are trying to say state space models is slightly better than recurrent neural networks, as they relax these stable approximation issues, and this can partially contribute to the performance. And actually we can see it in the optimization component. That is we give the following gradient bound. So we consider just the recurrent weight. So F is the representation that we are using for the recurrent weight. So that is H dHT dt equals to F W HT plus UXT. So F is the representation function F we are using, and the gradients of weight W is bounded by the right-hand side. That is, the recurrent weight gradient is bounded by a coefficient times a conditioning factor. This coefficient is independent of the representation. Therefore, it's just task dependent. So H is the task we are approximating. But the second term, f prime over f squared, this is a conditioning factor induced by the reparameterization function f we select. Therefore, by choosing a suitable reparameterization function, we will have a proper conditioning factor for the gradient bound. And we know that recurrent neural networks suffer from a classical issue, that is the vanishing and exploding gradient. Then if we have suitable upper bound from the conditioning factor, then we can actually relax these exploding gradient issues because we can just bound it with some constant. And then this representation F actually influence the loss landscape and serves as a relaxation. And here are the numerical verification. We train the language modeling over a classical wiki text dataset. It's a language models task. And here we are showing that these two are unstable representation, while these four are stable, just based on the logarithm of f absolute value criterion. So just based on this criterion, we know that the right four are stable and the left two are unstable. And when we evaluate the gradient over weight ratios, we can see that for the first two, their gradient range is very large, as the smallest gradient is 10 to the power of -8, while the largest one is 10 to the power of 1. So it's like they have 9 scales. But for the right side, these fours are all stable representations, and they manage to narrow down the gradient scale, and hopefully this gives a better optimization stability. So this is the reason.
I have a question, because here the soft plus is better than the best.
Yes, so that's why I say that actually we are proposing this best, but we can see that the best is not optimal in a particular scale sense. It's just the best representation can come with a gradient bound. That is, we can have this bound to be as an infinity for all w. If f is f best. So it's just we are proposing the representation based on the gradient scale criterion. But during the numerical experiment, we are just having difficulty to see the significance of this method. But we do have a strange task, that is we want to further scale up this model and then using a very large learning rate. Then you can see the power of this best. But I guess there is not much people tuning the parameters in this this approach. That is, people will always try to use some small learning rate, and usually the best representation does not give much benefit. Okay, so this is the empirical evidence to show that the stable representation is helpful to achieve the a scale up of state space models. And here we come to the conclusion of this talk. That is, when model is sufficiently large, we can see that actually recurrent neural networks and vanilla state space models, they both suffer from the exponential decaying memory issue, while stable SSMs, by introducing a representation, they relax this constraint. And based on the stable approximation setup, there are actually a lot of future works to consider. For example, just mentioned by the prof, we can consider like whether Mamba or some model variant can relax the exponential decay of vanilla state space models and achieving the polynomial decay, because for stable SSM, the model space is not changed. But for Mamba, they introduced this gating. Therefore, hopefully the model space is larger and they have some true polynomial decaying memory models in the model space. And there are several other interesting questions, like whether state models can do the length extension well from the perspective of generalization. Okay, so that's all from my today's talk. I'm open to any questions.
Thank you so much, Shida, for your great talk. And thank you for staying awake. I think it's around 2 a.m. in your time zone. So now we open the floor for questions. Do we have any questions for the speaker from the audience? George, do you want to?
Yeah, I'll have one more question.
Comment?
Shida, thank you very much. Very good talk. So are you familiar with these CANs, the Kolmogorov-Arnold networks that recently appeared?
Yeah, actually, I read the paper, but I'm not very familiar with the detail.
There's a claim. Yeah. There's a claim there, and they have an example that CANs don't forget. It's not a theoretical claim; it's an empirical claim. But I wonder why is that? Because they're changing the representation, right? But nothing to do with. They don't talk about stability. I don't see how this change of basis will change the stability. Actually, the basis. Let's see. If you change the basis in classical numerical methods, in principle, you change stability. Yeah, okay. But yes. I don't know here. Have you seen that part? Because that will be really interesting to investigate if indeed we don't have any evidence. I don't know if Juan is working on this, if he has tried any, and Nazanin, if they have tried any examples.
Yeah, I did one example with B-spline. It doesn't forget, but for like Jacobi and Chebyshev it happens. The forgetting happens.
Okay. One concern I have is like for neural network, once it is finite dimensional, then the information can be kept with finite dimensional space is limited. Therefore, I guess they still need to like forget in the asymptotic approach, like when we have the sequence length grows.
Yes.
Oh, right.
And I think this problem is a little different because I don't know, it's deep sequence model, right? It is different from neural network. That's what we are doing. Here the problem is different, and I think, for example, Mamba doesn't have the memory issue because it is updating the matrices that are like a kind of coefficient for the hidden space with an algorithm. So it is not, I don't know, it doesn't have a memory issue because it is updating all of them with an algorithm. So it can update, like it can put the values in each time step based on the algorithm.
Yes, for the Mamba case, it's like probably they have improved the model space. Otherwise, just improving the optimization part probably does not give that much benefits.
Regarding the
go ahead, Juan. Yeah.
Regarding the GAN and their ability to remember in some sense, I think that in the paper they mentioned something that it was somehow like by design, like GANs are able to represent things with fewer edges. So in the GANs, not every single neuron has its saying, like not every single neuron will be activated. There will be a lot of dead neurons once you reach to the final stage. So why you can relearn is because since you have many dead neurons, you have new paths to get new to find new connections. And I think that that's what I was saying, that maybe that's by design. It's because, for example, when they have like the thing that they call multi-quit, that they have at the beginning of training they use only 3 quits, because in the basis can be, they can be local, they can be global as in Chebyshev cans, or they can be local as when you use the baseline. So when you use like the local basis, you can expand them later, as which means that you have more paths there. So why they can learn is because they will, let's say that you have a complicated network, but only, I don't know, 30% of your neurons will be telling you something, but your 70% will be zeros. So if you have a new task, that's what they claim, that the remaining 70% will be learning the new things.
Yes,
Yeah.
okay. It's
Yes,
like
Juan is right.
hidden dimension is M, but like as you mentioned, maybe 30% of M is used and the rest are still available for learning. But I guess it is limited to the case that the hidden dimension is actually large for this task. Like we are working with the over parameterization setting. But for I don't know, for sequence modeling, actually the sequence length can be infinite. So in some sense, recurrent models are not working with the over parameterization setting, because we want to use finite dimension M to approximate an infinite sequence. Like the row is like the 0 to infinity.
Yes.
So
And I agree with
yeah.
Yes, and I agree with Juan. It depends on the problem that we have and how, I don't know, how much we are going in time and claiming that it doesn't forget. And it depends on the size of the neural network, not neural network, the network, the architecture that we are claiming that it doesn't forget. But for Chebyshev and Jacobi, we had the forgetting problem. And you're
Yes.
right. Here, yeah, it's a little different.
Okay.
Any other comments, questions? George, do you have any comment to?
No,
No,
thank you very much,
okay.
Shida. Thanks for staying up.
Yes. Thank you so much. So it's time to close the session. Thank you for joining us today. And thank you everybody who attended the seminar. I hope everybody has a great weekend ahead. Bye.
Thank you,
Bye.
Shida.
Yeah, thank you.
Bye.